In this lecture, we're going to be going over the margin of error percent, and the confidence interval when we do not know the population standard deviation, and thus we are going to be using the t-distribution. So let's go ahead and get started. This is what we're going to be doing. We are, like I said, calculating all this, and so you can go through these learning objectives in your notes. So what is the t-distribution? Great question. First of all, we have a normal distribution, which is the z-distribution. Then we have the t-distribution. The z-distribution follows the empirical rule perfectly. You're able to use the z formula to be able to calculate probabilities, and it's pretty precise because it's like, hey, we have the normal distribution, we have this population data, and we're able to be very precise with what it is that we are predicting, or that we are anticipating, the probabilities, if you will. But the t-distribution specifically is a little bit more conservative. So I'm not going to say less precise, I'm going to say more conservative. And the reason why is because we don't know the population standard deviation, and because we don't know the population standard deviation, by default, it's just going to be more conservative, so that way we can have a better estimation of what it is that we're doing. It is mound-shaped and it is symmetrical. Very similar to the Z, but it's a bit flatter and more spread out than the standard normal distribution. And there's a family of t-distributions depending on how large the sample size is. If you have a larger sample size, the larger the sample size, the closer it gets to being a z-distribution. The smaller the sample size, the further away it is from being a z-distribution. But at the point of at about 200, a size of a sample of about 200 or more, the t-distribution is more or less identical to the normal distribution. So you can use the z at about 200 or more, and so it really doesn't matter at that point. Just use the z, and it's going to make your life a lot easier. So, quick quiz. What should I use when? So I've got 3 examples below, and the first one is I've got 256 students' GPAs. The average GPA is 3.145, and I've got the sample standard deviation of 0.23. So looking at all this information, it's like, what should I use? Looking at the previous slide, you know that when you only have a sample standard deviation, you should be using the t, right? But your sample size is very large, and so your sample size, because your sample size is very large, it doesn't matter. It does not matter if you use the t or the normal. Use the t or the z score. Either one will give you the exact same answers because your sample size is so large. So go ahead and use the z or use the t. It doesn't really matter. Next, the height of 10 volleyball players. You've got the mean of 70.145 inches with a standard deviation of 2.65 inches. So the number is 10. That's how many people you have. So you have something called degrees of freedom. And so with degrees of freedom, that's going to be 10 minus 1. And so that's going to give you the degrees of freedom of 9. So what should you be using? T. Use a t, and the reason why is because it's a small sample size with a sample standard deviation. Next, salaries of 45 students post-graduation. So we have a mean of those 45 students of $55,343 with a standard deviation, a population standard deviation of $3,245. So what we should be using then is we should be using, because we have a population standard deviation, we should be using a normal or a z-score. So we have the population standard deviation, which is known. And so that's what we have right there. So when we know the population standard deviation, use the normal or the z-score. When we don't know it and we have a small sample size, use a t. And when we have a large sample size, it really doesn't matter. Okay, so when we are calculating the margin of error, so on and so forth, when we don't know the standard deviation, like I said, we're going to be using a t distribution. And so when we use a t distribution, the formulas to calculate the margin of error, the percent margin of error, and confidence interval are slightly different. Like I said, we're going to be using a t-distribution, and so the big change is instead of a z-score here, you're going to be using a t-score, and the t-score is obtained a little bit differently. Like for instance, when this is an example of when we would use the T score, a real world example. The dean of the business college wants to estimate the mean number of hours full-time students work at paying jobs each week. He randomly selects a sample of 30 students and asks them how many hours they worked last week. He can calculate the sample mean, but it's unlikely that he would know the population standard deviation, so we must use the T distribution instead. So like I said, we've got the t distribution right here, and in order to calculate the t distribution, what we need to do is we need to pull out your t table. Now, I make the t table available to you on Canvas, and so I would encourage you go to Canvas under Unit 3. Let's see here. We are going to go to Canvas. Under Unit 3, scroll on down, and go to 321, and scroll on down, and you can download the T-chart right there. And so I'm going to pull up the T-chart really quick, and we've got this T-chart right here. So here's what you need to do. We're going to follow a few steps. First thing that we need to do is we need to, at the very top, we need to find confidence interval. So we see CI right here, confidence interval, and what confidence interval do we want? You either want an 80, 90, 95, 98, 99. Just make sure that you're following these values right here for the confidence interval. These are for something else. The 0.01, these are for levels of significance, and this is going to be for the next unit. So don't use these yet. Use the confidence interval right here. So let's just say that we're going to have a 95% confidence interval. We want to have a 95% confidence interval. We seem to use that one a lot. That's just because a lot of people use that one a lot. It's good. So the next thing that we need to do is we need to determine the degrees of freedom. The degrees of freedom for a confidence interval, the formula for that is literally n minus 1. N minus 1. So degrees of freedom equals n minus 1. So what is n? N is the number in the sample. So let's go to the previous slide. And in the previous slide, we are going to see, okay, they've got a sample of 30 students. So because they have a sample of 30 students, we're going to come in here and we're going to say, okay, we've got a confidence interval of 95, and we are going to scroll on down to where we see 30 students. Now, we don't do 30 though, because we have 30 students, the degrees of freedom is 29. Okay, so we've got 29. And we find the intersection of 29 and, let's see here, 29 and 95, which is going to come right down here. So this is the intersection of 29 and 95. So instead of a z-score, so what would a z-score be? A z-score would be 1.96. This is a t-score, so it's going to be more conservative. And this is every single t-score when you have samples of 30 and you're looking for a confidence interval of 95. And so this is the score, or this is the t-score for that, of 2.045. So here you would put 2.045, 2.045, 2.045. So you just put that t-score into the formula, and then you have the standard deviation divided by the square root of n divided by x bar, so on and so forth. So here's another example using the t-table. So if we have a sample of 10, say we have a sample of 10, using the t-table, move across that the columns identified as the confidence interval, so move to 95. In the next example, we're going to use the 95 confidence, so move to that column and find the degrees of freedom. So right here we should have, let's see here, n equals, we're going to do n equals 10 for this example. N equals 10. Let's see here. And then degrees of freedom is n minus 1. Okay? So that is 9, n minus 1. So 10 minus 1 is 9. And we find the intersection, so it's going to be 2.262. So here we've got another real-world example. A tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.23 inches of tread remaining with a standard deviation of 0.09 inches. So in other words, they took a sample of 10 tires. They want to know how much tire tread is still remaining after driving 50,000 miles. And the average amount remaining was 0.32 inches of tread that was remaining, give or take 0.09 inches, or with a standard deviation, sorry, not give or take, with a standard deviation of 0.09 inches. So constructing 95% confidence interval with a population, for the population mean. So this is a point estimate of the population mean, but in order to do a point estimate, a point estimate of the population mean with the confidence interval, so in other words, an interval estimate, if you will, would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.3 inches? Well, as long as 0.3 inches falls within that your confidence interval that you are constructing, then the answer would be yes. But let's see. So we have the mean. So we're going to put the mean right there. So the very first thing that I'm going to do is I'm going to calculate the margin of error. Okay, so I'm going to put the margin of error, let's see here. Margin of error is going to be right there. Let's bring this down. So this right here is the margin of error. Remember at the previous slide, we have the 2.262 is the t-score. And so we've got t equals 2.262 multiplied by the standard deviation of 0.09 divided by the square root of 10. Okay, so if you work that out, that means that the margin of error is going to equal 0.064. Okay, 0.064. And if we were to calculate the percent margin of error, we would do the mean, or sorry, that 0.064 divided by the mean, which is 0.32. So let's do that really quick. Control C. I'm gonna put this into Excel, and then divided by 0.32. And that's going to give me 0.2. So the percent margin of error, percent margin of error equals 0.064 divided by 0.32, which equals 0.2. Okay, so the margin of error is basically 20%. So now that we have this, we want to know what the margin of error is here. So now we've got plus or minus 0.32 plus or minus 0.064. So this gives us the margin of error. And then for the confidence interval, which is right down here, we subtract 0.064 from 0.32, and that gives us 0.256, and then we add 0.064 to 0.32, and that gives us 0.384. So because the confidence interval is, what's that called? Because the remaining, they're wanting to know, does 0.3, is it within, is it a reasonable thing to conclude? Is it reasonable to conclude that 0.3 is the amount that amount of tread that's remaining? And the answer is yes. And the reason why is because it's within the limits of the confidence interval. So the endpoints of the confidence interval are 0.256 and 0.384. The margin of error is 0.04 or 0.064. So the manufacturer can be reasonably sure, 95% confident, that the mean remaining tread depth is between those two values. Between the value, because that value is in that interval, it's possible that the population mean is 0.3. Notice we're not saying that it is, we're saying that it's possible that it is. Okay. So going off of the previous, what's that called? The previous lecture that we had, I did this this thing with FIFA, right? With FIFA, I once again I told you, hey, when we have a 95% confidence interval, we are saying that if I take 100 samples, then 95 of those samples, the confidence interval for 95 of those samples will contain the population mean. But for 5 of those samples, it probably won't. And so that's what the 95% confidence interval is. So what I did is I've got these samples of 10. Okay, so I've got all these samples 10. I've got the mean, the average height of 10 players. So this right here is the average height of 10 players that play soccer, 10 soccer players. And so, we already know the population mean, and we already know the population standard deviation, but we also know the sample standard deviation for all those samples of 10. So if I'm looking at specifically, I'm going to hide this, and then I've got samples of 10, hide, and once again we use that same t-score, which I'm using a slightly different way to calculate it. Notice how accurate this is, this 2.262. The reason why is, and you should pay attention to this formula right here, okay? What this formula is, okay, equals t dot inverse dot 2tail, 2t, okay? And I'm going to do the probability. So the probability is 0.05. Notice it asks for the probability. It does not ask for the alpha. If it asked for the alpha, then you would put 0.95. But because it asks for the probability, what it's asking for is the probability of it being beyond those values. If you ask for the alpha, you're asking for the probability of it being within those values. But right there it says probability, and then the degrees of freedom is going to be the number of observations minus 1. Okay. And so that's going to give you the t-score, and it's going to be much more accurate, and it's also going to be very quick. So now what I did is I've got the standard deviation, the sample of 10, and we're going to hide this. And so we've got the standard error, the population standard error, but we can't use the population standard error because theoretically we don't know the population standard deviation. So I'm going to hide this, hide. So now we have to use the standard deviation for each one of these samples. So each one of the standard errors is going to be slightly different. And so each one of the margin of errors is also going to be slightly different because the standard error is or the standard deviation is different, the standard error is different, the margin of error is different, the percent margin of error is different, everything is different. And so now we have the exact same mean, but because we're looking at the sample, the sample standard deviation instead of the population standard deviation, look at the sample standard deviation compared to the population standard deviation, the margin of errors, and when you work with the sample data, we're going to try to be much more conservative, so that way we're going to be more accurate if we have extreme outliers, so on and so forth. And so this is what the confidence interval would look like when using the sample, and this is what the confidence interval levels limits would look like when we're using the population standard deviation. And notice that this is wider than this. It's not always going to be wider. Sometimes it's going to be narrower. It all depends. Okay, but coming over here specifically, I did the exact same thing that we did earlier in the previous lecture, but with the blue, Notice the light blue is the bottom limit, the dark blue is the upper limit of the sample, uh, standard, of the sample distribution. So with the t distribution, sorry, and then the yellow and the orange is with the population standard deviation, and so the we're going to be more conservative, and almost all the way across you'll see it's a lot more conservative, and the t distribution is going to be wider, more spread out than the z distribution. And so with the z distribution we're able to be a little bit more precise because we know the population standard deviation. So just be very aware of that the z distribution is more precise and the t distribution is less precise, and the reason why is because we know the population standard deviation, and so therefore we're able to be more precise. Hopefully this was beneficial. Once again, if you go across, you'll see that about 5 out of the 100 in here, 5 of the sample confidence intervals do not contain the population mean for either the z distribution or for the t distribution. And so it's pretty much the exact same thing. It's just more conservative, and it's dealing with the sample standard deviation instead of the population standard deviation. Cool. Well, hopefully this helps, and if you have any questions, looking forward to answering them via GroupMe or on our upcoming meeting on Wednesday.